You see smoke rise and you think light things go up, heavy things go down. That's the instinct. It feels obvious. Helium balloons float, rocks sink, smoke drifts upward. There's a natural order. Gravity sorts things by weight. But stop and think about what gravity actually does. Gravity pulls. That's it. It's an attractive force between masses. The Earth pulls on you. You pull on the Earth. Every atom in the smoke, every molecule in the air, every particle in the room is being pulled downward toward the center of the planet. Gravity does not push. It has no mechanism for lifting. There is no anti-gravity zone that makes light things float upward. The force is always down, always attractive, always pulling. So if gravity only pulls down, then why does smoke go up? You might say, well, smoke is lighter than air, so gravity pulls on it less. Fine, but pulling less is not the same as pushing up. If you pull on something weakly, it still moves in the direction you're pulling. It just accelerates more slowly. If gravity is the only force, then smoke should fall. Slowly maybe, gently. But it should fall. It doesn't. It rises. Against the pull of gravity, moving in the opposite direction of the only force you think is acting on it. So there must be another force. An upward force. Something pushing the smoke from below or pulling it from above or otherwise overcoming gravity's downward pull. You call this buoyancy, and you've been told it's a force. The buoyant force, it acts on objects immersed in a fluid. If the object is less dense than the fluid, the buoyant force is greater than the gravitational force, and the object rises. That sounds like an explanation, but it's not. It's just a name for the thing you're trying to explain. What is the buoyant force? Where does it come from? What exerts it? You might say, the fluid, the air. The air pushes up on the smoke. Fine. But why? Why does air push up? Air is made of molecules. Molecules are pulled down by gravity, just like everything else. If air is falling, how can it push something upward? This is the question no one asks. And it's the only question that matters. Gravity pulls everything down. So where does the upward force come from? Here's what you need to understand. The air around the smoke is heavier than the smoke, not hotter or colder, not thicker or thinner, heavier, more mass per unit volume, denser, and density matters because of gravity. Gravity pulls on mass. More mass in a given volume means more gravitational force on that volume. The denser air is being pulled down harder than the smoke, so the air falls, not all at once, not like a collapsing ceiling. But statistically on average, the air molecules are accelerating downward under gravity. They want to occupy the lowest positions they can. They want to sink, and the smoke is in the way. The air can't fall through the smoke. Matter doesn't pass through matter. The air molecules collide with the smoke particles, and when they do, they push. They exert pressure from the sides, from below, from every direction. But here's the key. The air below the smoke is denser than the air above the smoke. Why? Because gravity. The weight of all the air above compresses the air below. The atmosphere is denser at sea level than it is at the top of a mountain, denser at the floor than at the ceiling. The pressure increases as you go down because there's more air piled on top, and all that air has weight. So the air below the smoke is not only falling, it's denser, which means there are more air molecules below the smoke than above it, which means more collisions from below than from above. And collisions are forces. The air molecules below the smoke are crashing into it, pushing it upward. The air molecules above the smoke are crashing into it too, pushing it downward. But there are more molecules below, more collisions, more force. The net result is an upward push, not because anything wants the smoke to rise, not because the smoke is special, But because the denser air below is being pulled down by gravity, and the smoke happens to be in the path, the air is trying to get lower, and the only way it can do that is by displacing the smoke. So the smoke rises, not because it's light, not because it's hot, but because the air around it is heavy, and that heavy air is falling, and the smoke is simply being shoved out of the way. This is buoyancy, not a lifting force, a displacement. The denser fluid falls, the less dense object gets pushed aside. And aside in a gravitational field means up. Feynman saw this clearly. Buoyancy is not about objects rising. It's about fluids sinking. The smoke is just marking the spot where the air couldn't fall because something less dense was in the way. You think of pressure as a force, as something the air exerts, a push, a field of influence surrounding objects, squeezing them from all sides. But pressure is not a force. Pressure is a statistic. It's the average result of trillions of molecules, each one moving randomly, each one colliding with surfaces, with each other, with anything in their path. Every collision transfers a tiny bit of momentum, a tiny push, and when you add up all those pushes over a given area, you get pressure. Pressure is just collision rate times momentum transfer. More collisions per second, higher pressure. Faster moving molecules, higher pressure. It's not a substance, it's not a thing the air has. It's a measurement of what air molecules are doing when they hit something. Now here's what matters. Pressure is not uniform. You think of air pressure as this constant, omnipresent value. 10320 pascals at sea level. 1 atmosphere. The same everywhere in the room, but it's not. It can't be. Because gravity is pulling on the air. At the floor, there's more air above you. The weight of the entire atmosphere is pressing down. That weight compresses the air at the bottom, packing the molecules closer together. Higher density, more molecules per cubic meter. And more molecules means more collisions. If you put your hand at floor level, more air molecules hit it per second than if you put your hand at the ceiling. Not dramatically more, the difference across a room is tiny but measurably more. The collision count is higher at the bottom. That's the pressure gradient. Pressure increases as you go down, not because the air is pressing harder, because there are more molecules and they're colliding more often. Put a smoke particle in that gradient. The particle is being hit by air molecules from every direction. Random collisions, billions per second, from above, from below, from the sides. Each collision imparts a tiny momentum kick. If the collision rate were the same from all directions, the kicks would average out. The particle would jiggle randomly Brownian motion, but it wouldn't drift in any particular direction. But the collision rate is not the same. There are more molecules below the particle than above it. More collisions from below. Each individual collision is random, but statistically, over billions of collisions per second, there are more upward kicks than downward kicks. The net result, the particle drifts upward, not because of a buoyant force in the classical sense, because the pressure gradient, the difference in collision rate between the bottom and the top, creates an imbalance. More momentum is being transferred from below than from above. This is the mechanism. This is what buoyancy actually is at the molecular level. It's not the air pushing the smoke. It's trillions of air molecules, each one moving randomly, colliding randomly, and the statistics of those collisions creating a net upward drift because gravity made the air denser at the bottom. Feynman understood this. Pressure is not a mysterious force. It's just molecules hitting things. And buoyancy is just the consequence of more molecules hitting from below than from above. The smoke doesn't know it's rising. The air doesn't know it's pushing. It's all statistics, collisions, and gravity setting up the imbalance. Let's be precise about how gravity builds the pressure gradient. Imagine a column of air. 1 square centimeter in cross-section, stretching from the ground to the edge of space. Every air molecule in that column is being pulled downward by gravity. Now consider a thin horizontal slice somewhere in the middle of that column. Air molecules above that slice are falling onto it. Air molecules in the slice are being compressed by the weight of everything above. This is hydrostatic equilibrium. The pressure at any height has to be strong enough to support the weight of all the air above it. If it weren't, the air would collapse. The atmosphere would compress into a thin layer at the surface. But the atmosphere doesn't collapse, it spreads out. And the reason is molecular motion. Air molecules are not sitting still, they're moving fast. At room temperature, nitrogen molecules are traveling at around 500 meters per second. They're colliding with each other, bouncing off in random directions, creating a diffuse cloud rather than a puddle. But gravity is still pulling, so even though the molecules are flying around randomly, they spend more time lower down than higher up. Statistically, they accumulate near the ground. This creates a density profile. More molecules per cubic meter at the bottom, fewer at the top. An exponential decay that follows from the balance between gravitational potential energy and thermal kinetic energy. And because density is higher at the bottom, so is collision rate. So is pressure. Here's the key insight. The pressure difference between two heights is exactly equal to the weight of the air between them. Take 2 points, 1 meter apart vertically. The pressure at the lower point is higher than the pressure at the upper point by exactly the weight of the air in that 1 meter column. This is not a coincidence. This is the only way the system can be in equilibrium. The pressure difference has to support the weight. If it didn't, the air would accelerate up or down until it did. Now put an object in that air, a smoke particle, a balloon, a rock. Doesn't matter. The object has a volume, and that volume displaces a certain amount of air. The air that would have been occupying that space is now pushed out. The pressure at the bottom of the object is higher than the pressure at the top, just like it was when the air filled that space. The object is being hit by more molecules from below than from above. The net upward force, the buoyant force, is equal to the pressure difference times the area, and that pressure difference is equal to the weight of the displaced air. This is Archimedes' principle, but now you see where it comes from. It's not a separate law. It's a direct consequence of gravity creating a pressure gradient, and pressure being a molecular collision count. If the object weighs less than the displaced air, the upward force from the pressure imbalance is greater than the downward pull of gravity on the object. Net upward acceleration. The object rises. If the object weighs more than the displaced air, gravity wins. The object sinks. If they're equal, the object floats. Neutral buoyancy. But in every case, the mechanism is the same. Gravity pulls on the air. The air responds by creating a density gradient. The density gradient creates a pressure gradient. The pressure gradient is a collision rate gradient, and the collision rate gradient produces a net upward force on anything less dense than the surrounding fluid. Smoke rises because it's less dense than air, and it's less dense because it's made of tiny carbon particles and water vapor and hot gases, all of which have less mass per unit volume than the nitrogen and oxygen surrounding them. The air molecules, pulled down by gravity, collide with the smoke from below more than from above. The smoke is pushed upward, not because it wants to rise, because the air wants to fall, and the smoke is in the way. Now let's destroy another intuition, the idea that smoke has some property that makes it rise. It doesn't. Smoke is just particles, tiny bits of carbon, ash, water droplets, unburned hydrocarbons. They have mass. They have volume. Gravity pulls on them just like it pulls on everything else. If you could isolate a single smoke particle in a vacuum, it would fall. Accelerate downward at 9.8 meters per second squared, just like a rock. There's nothing intrinsic to smoke that makes it buoyant. The only reason smoke rises is because it's surrounded by something denser. Replace the air with helium and smoke sinks. Helium is less dense than the smoke particles. The pressure gradient still exists. Helium molecules still pile up at the bottom under gravity, but now the displaced helium weighs less than the smoke. Gravity wins. The smoke falls. Replace the air with sulfur hexafluoride, a heavy gas, 5 times denser than air, and smoke rises even faster. The pressure gradient is steeper, more molecular collisions from below, stronger upward push. The smoke hasn't changed. Its density, its mass, its composition, all the same. What changed is the fluid around it, and that's what determines whether it rises or falls. Smoke is not rising. Smoke is being displaced. And here's the part that should reframe everything. The air doesn't care that it's smoke. The same mechanism works for anything. A helium balloon rises, not because helium is magic, because helium is less dense than air, and the air molecules, pulled by gravity, create a pressure gradient that pushes the balloon upward. A rock sinks in water, not because rocks are heavy, because the rock is denser than water, and the pressure gradient from the water isn't strong enough to overcome the gravitational pull on the rock. A wooden block floats, not because wood is light, because wood is less dense than water, and the water molecules colliding from below exert more force than gravity pulling down on the block. It's all the same mechanism, all the same physics. Gravity creates a density gradient in the fluid. The density gradient creates a pressure gradient. The pressure gradient creates a net force on any object with a different density than the fluid. The object is just a placeholder, a volume, a region of space that has a different density than its surroundings. The fluid doesn't know what's there. It only knows that something is displacing it, and it responds with the statistical result of trillions of molecular collisions. Smoke is visible. That's the only thing special about it. You can see it. You can watch it rise, and because you can see it, you think it's doing something. But it's not. It's passive. It's just marking the flow, revealing what the air is already doing. The air is falling. The denser air at the bottom is being pulled down, and in falling, it pushes aside anything less dense. The smoke happens to be less dense, so it gets pushed up. If the smoke weren't there, the air would still be doing the same thing. Falling, colliding, creating pressure gradients. You just wouldn't see it. Smoke is a tracer, a visible marker in an invisible flow. It rises because the air around it is sinking, and the pressure imbalance created by that sinking happens to push the smoke in the opposite direction. The smoke contributes almost nothing. It's not generating the force. It's not driving the motion. It's just along for the ride, carried by a statistical tide of molecular collisions that would exist with or without it. You've been told that hot air rises, and it does, but not for the reason you think. Temperature doesn't create buoyancy. Temperature changes density, and density is what matters. When you heat air, you're adding kinetic energy to the molecules. They move faster, they collide more violently, and because they're colliding harder, they push each other apart. The same number of molecules now occupies a larger volume. That's thermal expansion. Fewer molecules per cubic meter. Lower density. And once the density is lower, everything we've already discussed kicks in. The surrounding cooler air is denser. Gravity pulls on it harder. It sinks. The pressure gradient pushes the hot air upward, but the heat itself isn't doing the lifting. The heat is just changing the density. The mechanism, the collision rate imbalance, the pressure gradient, the displacement is exactly the same as it was for cold smoke or helium or anything else less dense than the surrounding fluid. You could have cold smoke rising through even colder air. As long as the smoke is less dense, it rises. Temperature is irrelevant to the mechanism. In fact, here's a thought experiment. Imagine smoke at room temperature. It rises. Now imagine you cool the surrounding air. The air contracts, it becomes denser. The smoke, still at room temperature, is now even less dense relative to the air. It rises faster. You didn't heat the smoke, you cooled the air, but the smoke rises more because what matters is not the temperature, it's the density difference. Hot air rises a shortcut, a correlation. Hot air is usually less dense than the air around it, so it usually rises, but it's not rising because it's hot. It's rising because it's less dense, and it's less dense because it's hot. The causation runs through density. Temperature is just one way to change density. You can also change density by changing composition. Helium is less dense than air at the same temperature. It rises. Carbon dioxide is more dense than air at the same temperature. It sinks. You can change density by changing pressure. Compress air and it becomes denser. It sinks. Decompress it and it becomes less dense. It rises. Temperature is one knob among many, and it's not even the fundamental one. Here's what Feynman would tell you. Stop thinking about hot air rising as a principle. It's not. It's an observation, a consequence. The principle is that denser fluids fall under gravity, and in falling, they displace less dense fluids upward. Heat just happens to be a convenient way to make air less dense, but you could achieve the same effect a dozen other ways. The smoke from a candle is hot. Fine, that makes it less dense. But even if you cooled that smoke instantly to room temperature, it would still be less dense than air because it's not pure air. It's a mixture of combustion products, water vapor, and particulates. Different composition, different density. So the smoke would still rise. Maybe more slowly because the temperature difference is gone. But it would rise because the mechanism has nothing to do with heat. It has to do with gravity acting on density gradients and creating pressure gradients through molecular collisions. Temperature is just a red herring, a distraction, a story we tell because it's easier than explaining the actual mechanism. But now you know better. Let's take this to its conclusion. You look at smoke rising and you think, that thing is floating. It's defying gravity, moving upward, lighter than air, free. But nothing floats. Not really. What you call floating is just being in the way of something heavier that's trying to fall. The smoke isn't rising on its own. It has no upward force acting on it from within. It's not propelled. It's not climbing. It's being shoved aside by air molecules that are falling under gravity and happen to be denser. Every object you've ever seen float is actually being displaced, pushed out of the way by a fluid that wants to occupy the lowest position it can and can't, because something less dense is in the space. A boat floats, not because water is lifting it, because the water is trying to sink, and the boat's hull is less dense than water, so the water pushes it aside. The boat is held up by the statistical pressure of trillions of water molecules colliding with its hull from below more than from above. A helium balloon floats, not because helium defies gravity, because air molecules are falling around it, colliding with it, and the collision rate from below is higher than from above, because gravity made the air denser at the bottom. Even you, standing on the ground, are being floated by the solid earth beneath you. The atoms in the floor are vibrating, colliding with the atoms in your feet, and those collisions create a pressure, a normal force that balances your weight. You're not floating, but the mechanism is the same. Molecular collisions from below, resisting the pull of gravity. Buoyancy is not a lifting phenomenon, it's a displacement phenomenon. Dense things fall. Less dense things get pushed out of the way. And in a gravitational field, out of the way means up. Smoke rises because air falls. That's it. That's the whole story. There's no mysterious upward force, no anti-gravity, no lightness principle. Just gravity pulling on everything, pulling harder on the denser fluid, and that denser fluid displacing the less dense smoke as it tries to sink. Feynman understood this completely. He saw buoyancy not as objects rising, but as fluids falling and objects happening to be less dense than the fluid, so they get pushed aside in the process. You'd never seen anything float. You only ever seen dense fluids fall in a gravitational field, and occasionally something less dense gets shoved upward as a side effect. The smoke doesn't know it's rising. The air doesn't know it's pushing. It's all just gravity, density, and the statistics of molecular collisions playing out across trillions of particles every second. And what you call rising is just the universe solving a minimization problem, how to arrange mass in a gravitational field such that the densest things are as low as possible. The smoke is not defying gravity, it's obeying it. It's just less dense than the air, so the air falls past it, and the smoke, by comparison, appears to rise. You thought smoke rose because it was light, because it was hot, because that's what smoke does. But smoke rises because the air is heavy, and the air is falling, and the smoke is simply in the way. Everything you thought was floating is actually sinking, just slower than the fluid around it. That's buoyancy. That's what Feynman saw. And once you see it, you can never look at rising smoke the same way again.